All right, we good?
Yep.
All good.
All good. Okay. Well, thanks everybody who's made it all the way to the final lecture. So today is just other topics. I didn't know how many other topics to include, so I included some other topics, and I'll try to finish at least the topics that I've included. Okay, so we're going to start with a common framework that unifies the ideas that we've looked at earlier in this series, and also give us some ideas for some new methods that would fit into that framework as well. I'm going to mention the Hermitian case, right? When your matrix is Hermitian or symmetric, you get a lot of simplifications in these algorithms, so that's worth talking about. Restarting has been a topic of discussion, so let's close that out with the discussion of deflation. I want to talk about matrix functions, which is another application of these Krylov methods. A little bit about Jacobian free Newton Krylov for nonlinear systems and other bits and pieces that I thought sort of fit along the way. Okay, so here's the common framework. We've got a matrix problem of some description in n dimensions. So we've looked at the eigenvalue problem and linear system. And we've got a subspace, and the star of this show, of course, has been the Krylov subspace. You can think of this as the trial space that you're going to project the problem onto. And so there are m degrees of freedom in this space. And then we've got a second subspace, which is essentially how we're going to impose m suitable constraints so that we can get a unique solution to this problem. Okay, so this is, if you like, the test space. And we've actually seen already two different choices for L, right? And we'll see how that has played out. Okay, so Arnoldi's method for eigenvalues has us choosing k equal to L. Okay, or L equal to k. So k is the Krylov subspace, and L is going to be the same thing. So how does this collapse into what we know and love about our Arnoldi method for eigenvalues? Well, what did we do? We found Ritz values, theta, and Ritz vectors, u, where u was in the Krylov subspace. Okay, so we've got, as usual, our basis, Vm, and vectors for this orthonormal basis. So y is the coordinate vector of one of these Ritz vectors. So the residual for this problem is u minus theta u. U is the Ritz value, or in terms of the small scale y's, avmy minus theta vmy. So what do we get if we impose that this is orthogonal to k itself? Okay, so we'll take our test space L to actually just be k. So this residual has to be orthogonal to k, so that means that Vm trend or Vm star times r has to be 0. All of those projections are 0. So we just put in our formula for the residual. The Vm star goes here, avm y minus theta vmy, and we'll see what falls out. So sure enough, we get our Vm star avm y are here, and this Vm star is going to kill off this Vm star to give you an I. So we get this projection that we know is H, projection of the matrix onto the Krylov subspace. And we've got the eigenvalue problem that we know and love. Okay, so the Ritz values come from solving this eigenvalue problem, which we now see is equivalent to this idea of a projection, okay, where L equals to K. Now, GMRes, which was our main method for solving linear systems, actually uses L equal to A times K. Okay, so we didn't derive GMRes in this way. GMRes has got the min res in it, right? So it's the generalized minimum residual. So sure enough, we derived it and motivated it by minimizing the residual. But an alternative way of looking at it is to once again project the problem onto K and then enforce that the residual, which in this case is the linear system residual, B minus AX or B minus AVMY, enforce that that is orthogonal to L. right, which is AK. Okay, so if that's true, then R is orthogonal to AK, so A VM star times R has to be 0. Okay, so now we can see we're going to use our Arnoldi relation. Okay, so AVM, we've got VM plus 1 HM bar. The residual is the linear system residual, as we've mentioned, so you put that in here. B is the first vector in your space, so it's beta VM plus 1 E1. Again, we see an AVM, so a VM plus 1 HM bar. Now we do the rearranging. Okay, so we get an HM star out the front here, a VM plus 1 star going with the VM plus 1 in here, so that's out. And we get an HM star HM, right, and the VM plus 1 again goes away with due to the orthogonality. But this we didn't solve this problem, did we? Right, HM star HMY equals HM star beta E1. I don't remember solving that. No, of course we did, okay? But we didn't do it literally by forming the normal equations. That's what these are, right? These are the normal equations for the least squares problem that we did actually solve. Okay, so in MATLAB, it just handles this for you. Just do a backslash on this rectangular system, you know, HM bar backslash beta E1. But at least conceptually, that is the same as solving these normal equations, which shows us that this is a projection method, not onto L, but not onto K, but onto L equals AK. Okay. So that's the two methods that we've studied in detail put into this framework, right? Both are built on the same K, the Krylov subspace, but the choice of L and naturally the form of the residual, right? Are you solving an eigenvalue problem or a linear system, determines the method. Okay, so we've got two entries in this table that could presumably have 4, right? The choice of the problem, equivalently the choice of the residual, and the choice of the L, right? Is it K or is it AK? Oh, well, we can't resist filling in the rest of the table as long as we're here then. So what would a projection method for eigenvalues that uses L equal to AK look like? Okay. And for that matter, what would a projection method for linear systems that uses L equal to K look like? In fact, let's do this one first, right? As long as we've got linear systems on the mind. So we've got our Krylov subspace K, and we're choosing L equal to K this time, right? So we're going to enforce that the linear system residual, which is the same as it was a moment ago, is orthogonal. Oops, I forgot to change this. That A shouldn't be there. Okay, so mentally cross that A out. That was a copy and paste omission. All right, so Rm is orthogonal just to K, but this is right. Vm star times Rm equals to 0. So this is an easier problem on paper because you've just got the Vm star multiplying by the residual. Okay, Vm star B, that's beta E1 for sure. Vm star AVM, we recognize this is HM. Okay, so this is a square linear system. Okay, so we end up solving the square linear system HM y equals to beta E1. And so this is a method. It's called the full orthogonalization method, but it certainly does not have that minimum residual property that we value so much in GMRes. Okay, so it's nowhere near as popular. In fact, it has its issues, but actually we're going to find a use for it. Okay, as long as I've gone to the trouble of making a slide, I better find a use for it today. So it will be back later on today. What also will be interesting in another context today is this missing square of the table. So an eigenvalue problem that uses AK for L. Okay, so there's an A here. The eigenvalue problem residual, AU minus theta U. Okay, so we're back to the eigenvalue problem, A VMY minus theta VMY. And all the constraints are imposed now that this residual is orthogonal to A times K. Okay, so that's A Vm star times Rim is equal to 0. Right, Ri, because you could have, multiple eigenvalues and eigenvector pairs you're looking for. They each come with a residual, okay? And so for any one of them, this condition is imposed. So what's that going to look like? All right, so we're going to have AVM, which is our representation of AK star times the eigenvalue residual. Okay, so this starts out feeling more like the GMRes derivation that we looked at before, because we're going to replace AVM with the full VMHM plus HM plus 1M, VM plus 1, EM transpose throughout. And then that word simplify is doing a bit of work. You know, it's Friday, so I didn't propose to go through each and every step of the simplification this time, but we're so good with this stuff now that you know, we'll be able to spot what goes on. All right, so if you had the VMHM and the HM plus 1 and all that in here and in here, then you're going to get HM star with HM, where the VM star with the VM became I. You're going to get a HM plus 1M squared when it operates on the corresponding term. And the HM star that's in here is going to end up over here as well. Okay. So this, you know, the theta yi term for the usual eigenvalue problem is inheriting a matrix of its own. Right, so it's got an HM star in there. And the new matrix you get over here used to be just HM, right, for the standard Ritz projection, is not at all just HM. It's HM star HM plus this rank 1 update. And so this is a generalized eigenvalue problem. Okay, so to calculate what are known as the harmonic Ritz values, and we'll leave the word harmonic just hanging there for now, but we'll give it some justification later on. You got to solve this generalized eigenvalue problem. That's okay. All right, still small, right? Still an m-dimensional scale of problem. MATLAB and most numerical linear algebra tools are fine with generalized eigenvalue problems. If not, and if this is not singular, you could multiply through by the inverse and do it that way. Okay, so these are just some different estimates for the eigenpairs of A. These are called the harmonic Ritz values and harmonic Ritz vectors, or at least the U that you get when you scale it up is the harmonic Ritz vector. Okay, and so that sits in here. Well, we preferred to start with talking about this, and I would say if you're reaching for a method to solve the eigenvalue problem, this is a good place to reach for. But we now see there's an alternative, and I promised to find a home for it today, so we'll see what we can use it for later. I would not reach for FOM if I'm solving AX equals to B, because why would you when this method right here is, you know, verifiably better? You know, it actually has a minimal property, minimizing the residual, and what's not to like about minimizing the residual? Okay, so just the terminology, if you're reading about this sort of stuff, you get Galerkin methods where you've chosen L equal to K, and you get Petrov-Galerkin methods, which is every other situation. L is just not K. For us, if L is not K, then it will be AK, okay, which is very natural in our context. Okay, well, we saw way back when we analyzed the Arnoldi method that the standard Arnoldi method tends to converge to exterior eigenvalues in the spectrum. And we did some great theoretical development where we looked at the polynomial minimization problem that method is truly solving. And maybe we're able to make a convincing argument that on the basis of that minimization problem, it's going to have to prefer exterior eigenvalues, and the interior ones get left right until the end. Now, maybe that's good. Maybe that is what you want, but suppose it's not, all right? Actually, if you want the smallest eigenvalues, what then? Okay, and in fact, we are going to want that at a point today. So look, one idea is just to apply the method to A inverse instead of A, all right? And this is true even if we went right back and used the power method. Okay, the power method wants to converge to the dominant eigenvalue. If you don't want that, if you want the smallest one, well, the smallest eigenvalue of A looks like the exterior eigenvalue of A inverse, or the dominant, if you're just looking at the very smallest. Okay, so the eigenvalues are reciprocals. And the eigenvectors don't change at all. Okay, so if you want to converge to these smallest eigenvalues, then what about just applying your Krylov method to A inverse instead of A? Okay, and just remember to flip the eigenvalue at the very end. I mean, that's fine. That's absolutely what you can do if you do sort of eigs or something like that in MATLAB, and you tell it to sort of focus in on the smallest, then it has to do this. Okay, so that means, this is not a free lunch by any means, you're going to have solves in building up your Krylov subspace, all right? No one's forming A inverse, of course, but this just really means solve AX equals to B, and then solve again, of course, not literally B, because we're building the orthonormal basis using the modified Graham-Schmidt as we go, but there's a solve every step of the way now, instead of just a matrix vector product. So, you know, half of this entire series has been about solving linear systems, right? So that's already a challenging problem in its own right. But if you happen to have a matrix for which, you know, a sparse direct method or something does the trick here, you know, like, you know, you've got a fast solve tridiagonal, or it's, you know, it's not so damaging when you factorize it, you know, the fill-in is under control. If you can manage a backslash, some sort of sparse backslash on these, then you're good to go, right? And you can localize the small eigenvalues in exactly this way. Okay, but of course, the cost of admission here is that you can cheaply apply A inverse times V. And in fact, this is completely general, right? So if you desire eigenvalues close to some particular value mu, then you should just use mu as the shift. Okay, you should look at A minus mu I inverse. Okay, because now the very smallest ones around the mu look like big ones, right, when you invert. Okay, of course, if you literally pick the eigenvalue, this would be singular, but you're never going to get you know, such a precise estimate to start with if you knew to start with why you're doing this. So if you know you're looking for eigenvalues around some mu, then you'd use this shifted inverse as well, right? So shifted inverse power method or shift inverse Arnoldi gets you what you need there, provided you can manage these solves. Okay, so that was a small detail, but we couldn't very well leave out that important tip in case you should require such a thing. But the other reason that I bring that up is because it does give us a nice interpretation of the harmonic Ritz values. Okay, so we should just go back and remind ourselves that's over here now. Okay, so it's the eigenvalue problem where the test space and the trial space are not the same. It's not Galerkin, it's Petrov-Galerkin. Okay, so L is equal to AK. But you get out a pair of, you know, Ritz values and vectors. So what do we make of those? Okay, so here's Ritz. This is where we started the series, right? This is the residual orthogonal to K. And then harmonic Ritz has us imposing the residual orthogonal to AK. Okay, well, see lots of A's times U floating around, so I'll just call that W, shall we? So W equals to AU. It's going to belong to A times K. Okay, so U is definitely in K, no matter what. This is Krylov subspace land, so the Ritz vector of either flavor belongs to K, so that A times U, which we call W, belongs to AK. So then reimagining this orthogonality condition in terms of W, okay, AU is W, U alone is A inverse W, and that is going to be orthogonal to AK. So bring the theta over here, theta inverse, 1 on theta, times W minus A inverse W, orthogonal to AK. So this now looks like an ordinary Ritz method applied to A inverse. Okay, because look at this. W belongs to AK, and the residual is orthogonal to AK.
Sorry,
so
Tim, what was the theta?
That's the Ritz value.
Oh, okay.
Yep. So this is our residual, right? If this was a true eigenpair, then AU equals theta U. So now where you see A times K, you see it here. That's the space where W lives, and it's the space that we apply our orthogonality conditions against. So this now looks like an ordinary Ritz method, except applied to A inverse. Okay, so the harmonic Ritz can be imposed in this way. It's not spectacular. Okay, let me be upfront about that. This is not a magic way to get spectacularly good estimates for the small eigenvalues without ever needing to apply A inverse. Okay, so it is a Ritz method for the eigenvalues of A inverse, but it still uses a space built up from A, not from A inverse. Okay, so this is not shift and invert, where we did a hard job of building up the Krylov subspace with A inverse. This is an idea, and that idea is why we call this harmonic Ritz. That's where the harmonic comes from, because we're looking at the reciprocal problem. And they are, in practice, observed to be somewhat better at small eigenvalues, but not at all comparable to a true shift and invert. But we are still going to find a use for this later on today. Okay, now on to the Hermitian case. So everything we've done really has been assuming just a general A, not terribly non-normal. So we've always been happy to use condition numbers of X and so on, and say that there's theoretical results that we can trust. But if you want the very best case for your A, especially if you're talking eigenvalue problems, then A equals to A star does give you considerable simplification in the Arnoldi method. Okay, most notably because the third Arnoldi relation, VM star AVM, is HM. And this, I seem to recall, we may have discussed in question time at some point. But, HM is upper Hessenberg by construction. And now, because A equals to A star, it's also Hermitian. All right, so it inherits the symmetry, if you like, from A, but it didn't stop being upper Hessenberg. And so what's an upper Hessenberg Hermitian matrix? It looks like this. It's tridiagonal. Okay, it must be. Okay, it's 0 below the first subdiagonal, therefore by symmetry it's 0 above the first superdiagonal. So there's really just scalars, alphas and betas, right? Still symmetric, right? So this number is the same, beta 1, beta 2, and so on. So nobody bothers to call it H, and nobody writes it out, as H11 and H12 and all the rest. They just use notation like alpha and beta, and you recast all of the numerical scheme in terms of alpha and beta, forming those components of the matrix. But I mean, look at the implications here. Most of the inner products that we would usually compute in the Arnoldi process must already be 0. Okay, we'd normally need to include them in our Hessenberg matrix. We'd have to work hard to calculate all these inner products and subtract away the projections and so on. But up here, it's just 0. It's just guaranteed to be 0 already. Okay, so you get 3-term recurrence relationships and links with other sort of similar things in maths. Orthogonal polynomials are in the conversation and so on. But, there's two worlds in which these methods live, of course. There's the mathematical, ideal world where, it says right here, all right, this matrix here is tridiagonal, so don't bother doing any further orthogonalization. There's just 2 vectors worth of orthogonalization to do at every step, maximum 2. Okay, the third entry, of course, is the norm. So that, if that's literally true, that would make this now an order 1 cost per iteration. Just subtract away projections onto 2 vectors. And so order m overall. So you don't get the issues that Chen was talking about with your vanilla type of Arnoldi process where you're building out the subspace by one vector at a time, and then you've got to orthogonalize against all the vectors prior, that starts looking like an order m squared cost, right? So we have restarting and things to get around that. If this is true, that's just not an issue anymore, right? So the Lagrange process, which is the name of this for the symmetric case, is not at all prone to such runtime or even storage blowouts. You don't need to even store the previous vectors to orthogonalize against because they're not needed. However, the reality is that we are relying on the mathematical enforcement here of orthogonality. It looks good on the page, but in practice, every single calculation is done in floating point arithmetic with round-off errors. And so in practice, loss of orthogonality can and does appear in the basis. And that's complicated, okay? And there's good reasons that you might worry about that. And there's, as it turns out, equally good reasons why you might not worry so much about that. And there's a lot of theoretical analysis that goes along with this process, as is often the case. The Hermitian case lends itself to much deeper analysis that we haven't got time to go into. But the moral of the story is you really don't want full reorthogonalization, even though that would absolutely recover the orthonormality of your full basis, because that just blows the cost right back out to order m squared, okay, which negates much of the advantage. So there are these selective or partial reorthogonalization schemes that are quite popular. And essentially people just know what to expect. Okay, so loss of orthogonality is a thing, and it does affect the calculations, but it affects them in sort of more or less well understood ways. Right? So you get things like ghost eigenvalues and things that you thought you had once and they turn up again and so on. But there are ways to control these things. So you do win. The summary there is you do actually still win, despite the fact that the loss of orthogonality is real. Okay, so now we just a whole second table appeared. Okay, so we've got the original table we had earlier with A not equal to A star and a whole new version of it with A equals A star and 4 new methods. Okay, they are the exact analogs of the ones above, but they all come with the benefit that the Arnoldi process becomes a Lagrange process, right? 3-term recurrence type of thing. So yep, if you're looking for the symmetric eigenvalue problem, you'd be looking here. And here's where there is a difference. Whereas I would always reach for GMRes, I don't know, I'd much reach for MinRes, because if you've got, as you often do, a problem that's SPD, okay, so the conjugate gradient method sits in here as the analog of FOM when you use L equal to K, and in that case, you get a very nice version of an optimality property that actually involves the error. Okay, so we had some conversations in question time about, can you monitor the error in these methods, even though GMRes naturally monitors the residual conjugate gradient. The SPD version of FOM actually monitors a version of the error in this A norm. Okay, so if you've walked into this series already knowing a Krylov subspace method, it was probably this one, although you may not have derived it that way or thought of it that way, but it absolutely sits in amongst the family. Okay, and it's the version of FOM you get, and it's great. But I'll say no more about, because we've got more things to do. Okay, so there's a topic of interest based on our question time yesterday. We have certainly seen that restarting GMRes can be necessary. So back to the non-symmetric case where you don't want to build up your basis potentially too big, either because of reasons of memory or of runtime. But it does seem a bit wasteful throwing away the entire Krylov subspace you've just spent all this time and work building up just to start over with a new initial guess. Okay, that is what restarted GMRes is, but can't help but think maybe there's more information that we could be salvaging. Okay, so there's a whole host of ideas along these lines, how to recycle some of the information that you could have extracted from this Krylov subspace of dimension m. Okay, and so the approach that I've chosen to focus on here is called GMRes with deflated restarting, or GMRes DR. I'll just say there are variants. There are absolutely variants that use methods other than GMRes, and arguably the way it all fits together can feel more natural. But GMRes has been our go-to, so I'll stick with it. There are other ideas of building a preconditioner that does this effectively the same job, right? So you take the information and extract information. You take the Krylov subspace, extract some information, build a preconditioner to use for the next cycle with a similar idea. But the common plan here is really just to estimate a few of the smallest eigenvalue eigenvector pairs. Okay, so we're using this Krylov subspace to solve AX equals to B, but we know perfectly well it's also quite useful at extracting eigen information. And we also know that small eigenvalues cause us trouble in convergence of GMRes. Okay, so this is a way that we can link the two key themes of this whole series together in one method. What if we build up our Krylov subspace with the first cycle of GMRes, and then we use the information from that space to estimate the smallest eigenvalues and the corresponding eigenvectors. So these will be some version of RITs. And as we've already alluded to, harmonic RITs seems like could be the better tool if it's the smallest eigenvalues that we're looking to get. And we know we're not going to get exact estimates, but the dream is anything is better than nothing. Okay, and there's lots of information in this Krylov subspace going to waste otherwise. So why not essentially a form of compression, take all of that information, extract it down to maybe just one harmonic Ritz vector to start with. And let's see if we can't get some improvements in our next cycle by using this information somehow. Okay, so this is the idea. Now, it does rely on a fact that we haven't mentioned to this point, which is that the GMRes residual vector and the harmonic Ritz residual vector are parallel. Okay, now, we haven't mentioned before because we didn't hear about harmonic Ritz vectors until earlier today. But, these two methods come from the same family. Remember, they both use L equal to AK, right? So GMRes sets this residual vector orthogonal to AK, and harmonic Ritz sets this residual vector orthogonal to AK, and they both belong to Km plus 1. Okay, we've seen the polynomial perspective of this many times now. So these are both vectors belonging to Km plus 1, just dimension m plus 1, and both orthogonal to AK, dimension m, right? So there's only one degree of freedom left, and that means they are necessarily parallel vectors. I guess I couldn't resist just doing one quick demonstration of this fact. So here is a completely random example with some eigenvalues, and this is us doing Arnoldi in the usual way, m equals to 5, build up our v and our h.
I don't see MATLAB, Tim.
Sorry, what was that?
Are you in MATLAB? I only see the slides.
Oh, okay. Gosh. Just a sec. Thank you.
Thank you.
How about now?
Now we're talking.
Okay, now we're talking. All right. Well, you didn't miss much. We've got a random 8x8 matrix with some eigenvalues, some real, some complex. And we've got the Arnoldi method with m equals to 5. This is just, of course, a baby example as usual. And here's GMRes, right? Classic least squares problem. This is rectangular. Here's my beta E1. Here's X. Okay, so that's good old GMRes. This is the residual for GMRes. And so this bit is new. Okay, so we can just briefly dwell on this. This is the harmonic Ritz projection. Okay, so it doesn't use HM. It uses this new matrix that we derived, right? HM star HM plus this extra term here. rank 1 up, it just affects the bottom entry. And this is generalized eigenvalue problem. Okay, so I takes the two matrices, H2 and HM transpose. And so you get y's and thetas, and then from the y's you get u's, theta is theta. And so I just took, you know, the real ones, which is the first, the second, and the fifth, and calculated their residuals. Okay, how well does A times U equal theta times U? So I've got 3 harmonic Ritz eigenvalue residuals, and I've got 1 GMRes residual, and indeed they are scalar multiples. Okay, so just the element-wise ratio of R. This one is a multiple of R, this one is a multiple of R, this one's a multiple of R. Okay. Now, does this slides again?
Yeah.
See the slides, okay. All right, so conceptually at least, if we had have started the next GMRes cycle with one of these Ritz vectors, then we multiply that by A as our next step, and this already includes the proper restart vector. Okay, so if we're restarting GMRes, the new residual at step 0 is the old one at step M, and the eigenvalue residual and the GMRes residual are just scalar multiples. So as soon as you've got a U and an AU, then you've got all of those. Okay, so both of these residuals lie in the span of U and AU. So, you know, there's a hope here, okay? These problems are closely enough linked that we might be able to get them to play together. Now, if this was a true eigenvector, call it U, then at the end of the next cycle, the new residual, as if by magic, will have no component at all in that direction. Okay, so GMRes will gladly take the opportunity when it can, in fact, it's forced to completely kill off any component of the residual in that direction, because it enforces the residual is orthogonal to AK, right? So if K literally contains an eigenvector, U, that's the same as belonging to A times K after all, right? A times U is a multiple of U. So U belongs to this space, GMRes is forced to take the component of the residual in that direction to be 0. Fantastic, okay? So that eigenvalue gives you no trouble from that point on, because it literally has no component in the residual, right? GMRes is then free to focus on whatever else is going on. Well, if that's the case, then better still would be to surely include multiple K of these, let's say, harmonic Ritz vectors, all stuffed at the front of the space, okay? Now, if you do that, then all of these residuals are all just scalar multiples of the GMRes residual. So actually what you still have is a Krylov subspace, right? You could start with some linear combination of these U's and build up the Krylov subspace by multiplication by A, and you would generate exactly this space. Okay, so this is still, and this, especially because we paired the harmonic Ritz with GMRes, we'd still have a genuine Krylov subspace method. Now, having said that, nobody's forming the space this way. In fact, we didn't even form the original Krylov subspace by literally multiplying by B and AB and A squared B. We did Graham-Schmidt. So you do the same here, all right? So this in practice, you would orthonormalize your harmonic Ritz vectors, right? And there's a thing called a Schur decomposition. That's just the right tool for the job. It also deals with the conjugate pairs. You get little 2x2 blocks. Everything's great. You would then orthonormalize your starting GMRes vector against each of those, right? So you're building up an orthogonal basis for the vectors you start with, and then you build out the rest of the space from there in the usual way. Okay, and you derive a generalized Arnoldi relation at the end of this. Still looks like AVM equals VM plus 1 HM bar, except that the top left portion of your new HM bar is completely full now, right? So the K plus 1 by K block comes from the orthogonalization work you've done here, but this, you know, it's K plus 1, so it's no big deal. It's just a handful of vectors. M is already probably small. In fact, all of this work you can do at the M-dimensional step, right? It just requires a bit more bookkeeping, but all of the orthogonalization and so on can be done at the M dimensions and then map back up. So it's actually pretty cheap to restart. You no longer have that R0 is just the first vector, but it's definitely in there. Okay, so if you want to know its representation in terms of that new Krylov subspace, you just calculate it, right? You just calculate the projection, and so this is the new least squares problem you solve at the next cycle, at the end of that cycle. Okay, and then update, and away you go. Okay, you've got a new Krylov subspace. You can try to refine your estimates of those Ritz vectors and so on. Okay, so this works splendidly well in many circumstances. So here's just one example I'll show about GMRes DR, deflated restarting for one of these matrix market examples. I use Jacobi preconditioning. So GMRes M is okay. But as we sort of alluded to in question time yesterday, the convergence of GMRes M is not so straightforward to analyze. It's not as if it just carries on uniformly. You can't rely on that. GMRes is doing the best it can to peel off these components of the residual that cause it trouble and to kill them off. So every time you restart, you are getting the benefit of whatever work GMRes did in the previous cycle to kill off those components of the residual, but you've just got one vector's worth. Okay, so if that's not much is happening inside your dimension M, then your convergence can sort of stall. But nor does it mean the convergence is sort of a regular progression at a certain rate. You can get speed ups where those components have more or less been deflated in the natural way. But you can accelerate this yourself, right, by actually pulling out some of those Ritz vectors and sticking them at the front. And so in this case, that convergence looks competitive with full GMRes. Okay, even though this is restarting every 60 cycles, just augmenting that space with 6 of the harmonic Ritz vectors has done a fantastic job at bringing this residual down, comparable to full GMRes. Okay, so you're getting this extra source of deflation by not throwing away the whole of the space. Okay, instead of restarting with one vector's worth of information, which is the R0, we're starting with another 6, right, which is those harmonic Ritz vectors. Okay, that makes sense. You give it more information and it can do a good job with it. Okay, so I really like that example. It really brings together the two methods, or the two problems that we've been using Krylov subspace methods for, eigenvalues and linear systems, and puts them in a single method that leverages the benefits of both. Okay, another sometimes very important property of Krylov subspace methods is that you get shifted linear systems for free. Okay, so we haven't had to lean on this up until this point, but in your application, if you happen to need to solve a family of shifted linear systems like this, then you just build the Krylov subspace for once, okay? Because it's the same space after all, right? The Krylov subspace of A with B is the same as A plus sigma I of B, and so the Arnoldi relations carry right over. So you build it up once, and then you just tweak the H as needed. So for that one-off cost, building the basis, you then get arbitrarily many cheap shifted solves. Okay, so in an application that calls for a whole family of these, that one-off cost can be made essentially negligible compared to the cheap cost of solving, arbitrarily many shifted systems after that. Okay, that was just one slide worth of fun facts. Now, onto the next application of Krylov subspace methods. So again, we're asked about this during question time at different points, and I'm happy to talk about it. What about matrix functions? Okay, so you've got a function of a matrix, and you could list a whole screen full of applications where you need functions of matrices, but here's just a few: exponential integrators for solving ODEs, fractional PDEs was mentioned at one point, Markov chains. Of course, there are many. And as is often the case, we may not really need f of a, but only its action on a vector. Okay, in that case, Krylov subspace methods are, again, available to help out. Okay, we do the usual thing. We build up the Arnoldi decomposition of A and B. We know the projection of our matrix A onto that space is H. So what could be more natural than proposing the Krylov approximation f of H? All right, the vector that corresponds to B is B to E1. There's the B to E1, and then map it back. Okay, if anything is going to be the right formula, it must be this. Okay, well, take my word for it, or further convince yourself by the following argument. There are many equivalent ways to define what even is a matrix function. You can do it through the eigenvalue decomposition and so on, but you can also do it for the Cauchy integral formula. Okay, so this is a standard result in complex analysis, but if you just take it seriously and imagine what it would look like if A was a matrix, it turns out to be equivalent to every other definition of matrix function. And therefore, matrix function times a vector looks like this. Hey, shifted systems. Look at that. All right, we're integrating around some contour enclosing the eigenvalues of these shifted systems. Okay, so what if you approximate each of these shifted systems, depending on Z, with a Krylov subspace method, let's say FOM, right? The full orthogonalization method, not GMRes. Told you FOM would have a role to play. This is its turn. It's time to shine right now. So for the shifted system, we just have one Krylov subspace. We just shift the H and we solve. Okay, so just replace this. This is a solve, right? It's not really an inverse. It's a solve. Inverse times B. So here's the solve here. Reformulate it so that it looks like one of these. And what do we see? All right, the beta VM out the front, and this matrix function of H, sure enough, multiplying E1. Okay, so it is exactly the formula that we would have guessed. And we observe that in the special case when F is 1 on Z, this is just FOM. Okay, so you can think of the linear solve as a matrix function, and the function is 1 on Z. Okay, now we do come to a bit of a challenge though, because how do we monitor our convergence, right? Unlike a linear system or not least squares, an eigenvalue problem, there's no natural choice for a residual. Okay, you can tell how well AX equals B, and you can tell how well AU equals theta U, but how do you tell how well F of A equals B equals what? What's the residual, all right? There's no obvious choice, at least in general. If you happen to be interested in the exponential, then there is a good choice, right? Because you can use what's called an ODE residual. Okay, since the exponential is the solution to this ODE, you can formulate the ODE, right, and look at that residual. Okay, well, you can follow through the steps, but there's no big surprise. The formula you get involves stuff we've seen before, the beta, the HM plus 1M, and this particular entry of the E to the TH. Okay, so EM transpose E to the TH E1, multiply the HM plus 1M, multiply the beta. That's the ODE residual for the exponential function. And here's us giving it a go. Here's e to the minus a times b. A is this classic tridiagonal gallery matrix. Okay, so it's like a 1D finite difference matrix. And it does even better than like A plus I inverse. Okay, so I actually solved this with GMRes. We've seen a shifted version of a matrix. This doesn't have any issues with eigenvalues around 0. This is the matrix you'd get if you did a sort of a backward Euler type approach to solve an ODE. If you just write down the solution in terms of the exponential and compute that, you actually do better. Okay, so the convergence of e to the minus ab is a lot better than just the linear system. And I just threw in square root of a in here. Not so good. Okay, but e to the minus a, this is, an observation that gives rise to the exponential integrator family of methods and Krylov methods applied to compute those. They really converge quite well. No preconditioning or anything. On the other hand, square root was terrible there, and perhaps we shouldn't have been surprised because, the Krylov subspace approximation by its nature is a polynomial-based approximation, and you shouldn't expect a polynomial approximation of square root to be very good when you've got, eigenvalues towards the 0 end of the spectrum, as we surely do. So that does lead to the idea of using these, and this is maybe the first time we don't have an ordinary Krylov subspace, an extended Krylov subspace, where you build up the space involving products not just with A, but with its inverse. Okay, so solves as well as multiplies. Again, that assumes you've got a cheap solve, but if you do, Again, you don't build it up literally from left to right. You start with a V and then you hit it with an A and a solve and an A and a solve. The bookkeeping is a lot more complicated, but the payoff is that things like square root do much better. Okay, so the extended Krylov subspace method on this square root function, square root of A times B, is converging, whereas the ordinary Krylov approximation barely was. Also not surprising is that you don't buy anything. You don't gain anything by using the extended Krylov subspace for exp because it was already doing great with a polynomial. In fact, you wasted your time building out the vectors involving the solve. You should have spent those building up more terms for the polynomial. Okay, so the right tool for the job. There's lots more to say about that, but at least we're aware these things are around. Okay, just a few minutes to finish in the spirit of letting you know about things that exist without going into the details. GMRes with preconditioning. Preconditioning is a real indispensable tool in GMRes. What if your preconditioner is actually not fixed throughout the iterations, but changes every time it's applied? An example would be the preconditioner for the M is also an iterative method, solved to some tolerance. Now, if that's true, then you can't just build up the space and assume that A M inverse Vm is Vm plus 1 H bar, because it's not. There's no such M inverse, all right? Instead, you have to keep track of a second set of vectors, right? You've got to record the Zs, which is the M inverse Vs. The M changed every time. And then the W, A times the Z, and then you orthogonalize the W. So after it all, you get two full matrices, right? You get a Z and a V. So you've just doubled your storage. Everything else flows through just fine. You solve more or less the same problem. And that gives you the flexibility now to vary the preconditional with each step. Okay, so that's called flexible GMRs. And just very finally, for nonlinear problems, all right, so you've got a Newton solver, right, to solve f of x equals to 0. Each step would have you solving a linear system, right, involving the Jacobian. And, well, what could be more natural than to try a Krylov subspace method? And you'll be pleasantly surprised when you do, because if we've learned anything, it's that Krylov subspace methods only require Jacobian matrix vector products. In this case, that matrix is the Jacobian vector products to build the Krylov subspace. But guess what? A Jacobian vector product is already a thing. It's a directional derivative. Okay, so you can calculate the product of the Jacobian with an arbitrary vector v, just a derivative, using, well, what's your favorite technique? Automatic differentiation, dual numbers, finite differences. You don't need to form this Jacobian at all. Okay, you've got your f, you take a derivative in the direction, and that gives you the next product you need to build up your Krylov subspace. Okay, so this gives you a Jacobian-free Newton-Krylov method. If you don't need a matrix for the preconditioner, right? If your preconditioner is itself a process of some sort, or it's trivial or what, then the whole thing could be literally matrix-free. Okay, and your Krylov subspace method does all the work, never actually seeing the matrix. It never really did. It only ever saw products with vectors, after all. You can even win a bit more, okay, just to explain this picture. Every time you take a nonlinear step, the residual will reduce at the nonlinear level, but to take that step, you needed to solve the linear system, right? And the point is, there's no need to oversolve the linear system early on throughout the nonlinear process. In other words, an early direction that's, at all decent will give you the same reduction in the nonlinear residual. So all of this work, bringing the linear residual down, is wasted. Right? If I'd have taken a couple of steps in GMRes, I'd have got an equally good search direction for my Newton step. And so it goes. Wasted work, wasted work. Only later on in the process does the work at the linear level actually pay off at reducing the nonlinear residual. Okay? So people have, thought about this, of course, and there are very much further efficiencies possible by just matching the accuracy of the inner Krylov solves to the outer Newton level accuracy. Okay, so early on in the process, when you're local linear model doesn't really look like the true function, and there's no point in getting super accurate directions. You don't get super accurate directions. You take a linear residual that is scaled by this so-called forcing term, or forcing factor maybe would be better, and that this gets updated as the iterations proceed. Okay, so by doing that, you don't spin your wheels wasting time at the Krylov solves early on, right? A short, rough approximation works just as well, and it's much cheaper. And so, for this example, this was some convection diffusion PDE. I discretized, almost every single matrix vector product, Jacobian vector product, paid off at getting these reductions. There's a little bit of oversolving here, right? It's just to do with, literally how you choose this factor and how you update it. Okay, so that's Jacobian free Newton Krylov, and that is the list of the topics that we have covered here in our final slide. We've covered the Arnoldi process that we use to do all sorts of things by now, especially for finding eigenvalues. We analyzed that in some detail, especially for solving linear systems with GMRes that we spent a lot of time on, preconditioning, which is a key part of that GMRes story. And today, a whole host of other related Krylov methods, this key idea of deflation, matrix functions, and various other tips and tricks that I thought of at different times to put in. And I spoke just a little bit too long, but thank you for your attention. I'm really happy to stick around for however many questions we get. And really thanks, and from Chen as well, for your attention and your attendance. I know some of you have been here every day, same time, rain or shine, so thanks very much.
Thanks a lot, Tim.
You're welcome.
Thank you. I have a question actually.
Yep.
Where does the name deflation come from?
That's interesting. The etymology of the term deflation. I mean, the sentence that you would hear spoken about is you are deflating the eigenvalues. All right. So the original spectrum of your matrix has some troublesome eigenvalues that GMRes will eventually get on top of, and if you let it run long enough, it will solve everything for you. But if you can deflate those eigenvalues yourself, essentially remove them from the spectrum to various degrees of accuracy, if you're just using harmonic Ritz, even what's observed is that very coarse approximations can actually be quite beneficial, and then with every further step, you may refine them more. Look, it's a big topic all on its own. Of course, you could be solving an eigenvalue problem, right? That might be the thing you care about. So you can deflate the eigenvalues that you've already got good estimates for, and then your Arnoldi process starts working harder on the ones that you would like to have next. Okay. So, Lanczos methods can be restarted with the same idea. Things like thick restarted Lanczos methods use the exact same idea, that you use the information you have to help deflate the eigenvalues that you either want to know less about or that you don't want ruining your convergence, and then it's free to focus on the rest of the spectrum from then. Does that make sense?
Yeah, thank you.
Great.
So Tim, maybe I also ask a question. So you were talking about Galerkin and Petrov-Galerkin. So, and for Petrov-Galerkin, so I guess the extended Krylov subspace is, one of the examples. But I believe there, I don't know, just I mean, out of curiosity, so it's not probably many spaces, different types of spaces. It's really just a little bit of variation with the matrix, right? So do you include inverses or not? But or is there some other extensions that are still useful for preconditioners, or is it just really limited to, say, the powers of matrices?
Yeah. So the family really, if we just go back to here.
Mm-hmm.
To a good approximation, this is the family of methods that, of course, there are variations within each of these boxes, but there's no big third L that has come across my desk where people have discovered that it's fantastically better than taking K or A times K, right? All of the favorite methods that you'll see in your favorite numerical software, at least the tried and true methods, are based on one or other of these ideas.
Okay.
Yeah.
I have another question related to nonlinear systems.
Sure.
So
Yeah.
if you have like, I think in your slides you had like, you wanted to solve for f of x equals 0. Yeah.
Yep.
But if you have like a nonlinear system, so a of x times x equals b, and you do a Newton, maybe you will have like solved for ak x equals ak xk equals b, and then the next step you can see your ak plus 1 to be a plus a small variation of the matrix dA, and then so can you I see that you can recycle the Krylov subspaces for AK by using them to precondition the next system, I guess. But could you somehow modify or update the Krylov subspace from the one built for AK and then to the one built for AK plus 1?
Yeah, I think your intuition about the preconditioner would be where I'd reach for first there. So, preconditioners don't have to be, that special. They certainly don't have to be the literal inverse of the matrix you actually have. If they're built upon something that is in some sense resembling the matrix you actually have, then it might do a great job. So wherever you've got these methods where another situation comes up, if you've got some sort of time stepping type process, and what they do there is they might actually form and factorize a Jacobian early on and use it as a preconditioner, but from that point on, it's still JFNK, all right? So the Jacobian is certainly shifting beneath your feet, but you're keeping this preconditioner based on information much earlier, and it continues to work. Continues to work well for many, many further iterations, and then only eventually when you monitor the convergence and so on, it seems like it's a bit out of date, you may then reform and factorize and then keep that held fixed again and so on. So as this, your Krylov subspace methods continue to solve slightly different variations of the same problem, the preconditioner continues to work well, even though it came from an earlier version of that same problem.
Okay, thank you.
Yeah. You have any last burning questions?
Well, the chat is no questions in the chat.
Oh, yes, keep an eye on it. Okay.
Yeah.
Oh, well, if that's the case, then Chen, you want to jump in and say bye to everybody as well? It's been a fun ride, isn't it?
Yeah. Thank you for the invitation to give us this opportunity to deliver this lecture series. It's quite good fun.
It has been tremendous fun.
Yeah, we also had fun during the whole week, so thank you very much.
Thank you. Thank you,
Thank
Nadia.
you. Thank you, everyone.
Ricardo, thank you as well.
Thanks a lot for accepting the invitation, and to all the students from here from Monash, and I know that they've had a lot of fun. And I'm sure that you will be available for offline questions as well later on. So thanks a lot. And yeah, this is a really fun topic, and I've learned indeed. Thank you very much.
Our pleasure. And yeah, we'll just emphasize that. Let these ideas sink in, and then questions that arise, just drop us an email and we'll be happy to talk more. Okay.
Thank you.
Okay.
All right. Thanks again.
See you next time. Bye.
Bye.
Bye, everyone.
Thank you.